Hello, welcome to lecture 3 in video 3 in our lecture Advanced Mathematic Modeling. In the last video I showed you this example of the throw of a coin where we were in principle not able to determine the outcome of the experiment, even if in principle this could have been a deterministic process. And then we said the only thing what we can do is that we can treat this as a stochastic event, and then we have to design a probability for each of the two outcomes. And now I want to look a little bit more closely. What does it mean, probability? What do we mean by this concept? So probability means we quantify the likelihood for the outcome of our experiment, the likelihood for an event. And so how do we quantify this? So we want to give the probability P for an event, and so we want to do this on a scale between 0 and 1. So we want that P is bounded between 0 and 1. And on this scale, this should give us the likelihood for the event. So if P is equal to 0, so we say here this is an event which is impossible. Event with probability 1 is certain. And when we're somewhere in the middle, we're somewhere in between. So we don't know if it's if it's possible or certain. So we quantify the likelihood. Now the question is, how can we obtain this probability? How do we how can we come to this? And here, so first, one insight is that probability we will always define as a ratio or a proportion. Probability as a ratio or as a proportion. And I want to show you two principal ways how we could come to this ratio. And one is maybe more a physical one, by repeating experiments. Let's assume again our coin, or we do something a bit more complicated. We don't have a simple coin. Maybe we have here a pin, sometimes called here Bernoulli pin. So we have this object, like this pin, which can land like this, or it can land like this on the floor. In German, Reißzwecke. And so here it's not so clear what would be the probability for this outcome or this. But again, there's only two possibilities. The pin can only land on the flat side, or it can land on the floor like this. So what can we do? So the main idea to determine the probability of the outcomes is to repeat the experiment very often. And this comes here from this what we have seen here. So every individual experiment I will not be able to predict, but in principle I could measure the number of black and white dots here and get some idea of the likelihood. or here I cannot repeat the experiment, but if I have many repetitions, I see some idea about the scatter, about the trajectory. So we have to repeat the experiment, and then we know, so we repeat this very often. Let's n, we call this the number of experiments that we have done. Or the number of throws of the Bernoulli pin, and then we define a quantity p of n, and this is now a ratio. We define this as a ratio of the number of these experiments where we found a tail, if we call this maybe tail and this we call head, and this is the number of experiments. So this will be n. So it's the ratio how often we found one of our outcomes in the number of experiments. And if we do this, we make a plot, the number of n, the experiments, here we have this p of n. And it's clear that this must be bounded between 0 and 1, because we can never have more outcomes tail than the number of experiments. So this ratio is between 1 and 0. And we start this, and maybe we do first one experiment, and we find tail, then we have here 100% chance to have tail. We do this again, and then we have maybe this point, and then we do this more and more often, and so we increase the number of experiments. Maybe here we have done 10 experiments, 20, 50, 100, and so on. But then after some time, what we realize, what we see, that this ratio, the fraction of experiments where the pin lands in the tail position, this approaches the value. So this scattering around, this gets smaller and smaller, and if we do this experiment long enough, so we will find here a number. And this number, so the limit for infinite many repetitions, this is what we call the probability. So we say then P, the probability for the event tail, is the limes for n goes to infinity of our P of n. Oh, sorry, you are a bit out of the window here. And remember, this is a non-trivial thing, that this is really converging to this. I mean, there you can have many discussions why should this converge to one number, but I mean, this is the outcome, the observation when you do such experiments. And so with physical repetition of some experiment, always prepared in the same way, we then can obtain the probability, and the probability is a ratio. Now when we want to do some mathematics, probability is defined a little bit different, but again as a ratio. So probability, that would be probability in physics, maybe now probability in math. mathematics. And let's now assume we have to have an example, we have a throw of a dice. Yeah. And so a dice, we have 6 possible outcomes. We can have 1, 2, 3, 4, 5, 4, 6. These are the possible outcomes when we throw a dice. And now we want to know what's the probability for a number which is smaller than 3. Yeah. So that the dice has a number which is smaller than 3, and you see this is just these two possibilities. Either the dice shows a 1 or shows 2. Yeah? That's the only possible outcomes. And now we say, in principle, of all these possible outcomes of the dice throw.
Tut mir leid, ich finde das.
Oh, here's suddenly Siri in my computer activated for some reason, so I was able to switch it off. So for all the possible outcomes of the dice, that if they in principle all have equal likelihood, and then we say the probability for this event P of this event equals, so there would be 2 over 6, and 6 is the number of all possible outcomes, and 2 is the number of all the outcomes which are in our event. So we see, in order to, again, the probability is a ratio, but in order to obtain this ratio, we don't have to make many repetition of an experiment. The only thing we have to do, we have to count the sizes of sets. We have here the set of all possible outcomes, and then we have the set which defines our event. And again, we come to the idea, we find that this P, if we define it as such a ratio, that we have again 0 smaller p smaller than 1. So let's try to formalize this and so generalize this idea from the throw of a dice to the very general situation. And then we say we have a sample space very often called omega, and this is the space of all possible outcomes of that's the set of all possible outcomes. In this example here, in the dice example, this omega would have been the set of the numbers 1, 2, 3, 4, 5, 6. Or if we would have here our coin, then omega would be simply the set of binary outcomes head or tail. So we have discrete sets, but there's also, we could have also, for example, if the outcome is a position of some point, then the point in a restricted space, then this omega could also be an interval. Yeah. Omega could, for example, be the whole interval between 1 and a length, for example. So it could be continuous. English continuous. So in order to define probabilities, we have to deal with sets and set theory, and there's always the distinction: do we have discrete sets or continuous sets? Okay, now how do we come to the events? So the event, for example, in this case, you saw the event was the outcome is 1 or 2. So events will always correspond to subsets of the sample space. So an event is a subset of our sample space. And formally we write this like this. A, the event is a subset of omega. And we can even go further and say every possible subset of omega is a possible event. In the example of our dice, in this example, the subset, this event was the set of the numbers 1 and 2. And now we can say what is the probability of an event and so the probability is a function which assigns every event, so every subset of our sample space, a number. So we say P, the probability, is a function now from some object F, that's the set of all possible events, and every event is attributed then the probability between 0 and 1. And this function F is the set of all subsets of omega, the set of all events. And now like if you go to measure theory and probability theory, the problems arise: what is this F if you have continuous sets, infinite dimensional sample spaces, and then what's the set of all subsets and so on. But in practice we don't care. So probability is just a function which gives every possible event, it gives a number. So every event A, every subset of our sample space is attributed the probability of this event. And now there are some rules. So for example, we have the empty set, the set which is empty, and this gets the probability 0. And then we have the probability of the whole sample space that has the probability 1, because like some outcome must be there, so that's really certain that one of the outcomes will be there. And now what's the probability for smaller, or for in general, for a certain event? And this is now, as I said, a proportion. And now we have to count what's the size of the set divided by the size of the sample space. And this means, these bars here mean the size of the set. So in a discrete set, it would just be the number of elements in the set. And if it's a continuous, it's an interval, that's just the area of volume. Or here in continuous, it's just the area of volume of this continuous set. So in order to attribute a probability to an event, we just calculate sizes of sets and have a ratio. And this is exactly what we did here. this example, in order to get the probability for the event the number is smaller than 3, we took the size of our event, which is 2, the size of the sample space, which is 6, and then we get the probability 1/3. If you want to visualize this, very often we use this Venn diagrams. So we depict or visualize the whole sample space from maybe such a rectangle. That's the sample space omega. And if we have some event, then this is a subset of omega, and this would be the area in the circle, that would be the event A, and then the probability of A is the area of A divided by the area of omega. And now we can also, let's say if we have, we can do all kinds of operations with sets. For example, we can look what's the complementary event, what's this, so the complementary event, typically called AC, CB complementary. That's just the difference of the sample space and our event. So that's just the rest of this. So if A is this blue area, the complement is just the rest. And then if you think about this, then you directly see the probability of complementary event equals 1 minus the probability of the event. And with such rules, now you can have different events, and then you can define all kinds of operations with them. And now there is all kinds of rules how to generate new events. Assume you have two events A and B in our sample space, and there might be an overlap. And now we have different ways to combine these events. We can take the union. So we say this is the union of event A and B is A and B, and that's, the union of two sets. Or we can have the intersection, and we say A or B, or we can have a difference, and we say A without B, and we have here the different events here graphically depicted as Venn diagrams. And now the question, how can we calculate the probability of these events? Take the first example, the union. If we have the probability for A and B, or sorry, of course a mistake, I hope you saw this. This is of course or, because you can be either there or there, and this is of course and. Sorry for that. Now if you have A or B, then the probability is the probability of A plus the probability of B minus the probability of the intersection, because the intersection we should count only once. And now if the intersection is 0, if this intersection is not there, this means we call this A and B are disjoint events, then the probability of the union, the probability of A or B, is just the sum of the probabilities. And so how does this go with the intersection? For disjoint events, we've seen that the probability of the union is the sum of the probabilities. For the intersection, we don't have such a simple rule, but we can just make a definition. We say events A and B are independent if the probability of the intersection is the product of the probabilities of the events. But this is a definition, but this definition coincides what we intuitively would call as events A and B are not related by any means. And finally, the intersection. Here's the rule for the intersection. The probability of A without B is the probability of A minus the probability of so the probability of the difference is then the probability of A minus the probability of the intersection. And if B is a real subset of A, then the probability of the difference is just the difference of the probabilities. So these are basically the 4 rules that we need, and with this we can easily calculate or compute probabilities of more complicated events, and you will see some examples in the exercises. But basically I assume you have seen this already. Let's give you just one example. Take this example, which comes from throwing dice in a board game. You have 4 throws of a dice, and so you can throw this 4 times. What's the chance that at least once you have the number 6? And so in general, if you not really sure about the probability, it's important that you really make yourself clear what's the sample space and really strictly calculate the size of the event and the size of the sample set, because very often the intuition can go wrong. So what in this example would be the sample space? So the sample space omega is the set of all tuples of numbers between 1 and 6, or all these tuples. Then we can calculate the size of this set. That's 6 to the power of 4, and you can calculate this is 1296. So there's over 1,000 different possibilities of the outcome of throwing a dice 4 times. And now the question is, what is the event A? That's again here is set, and this is the set of all outcomes where at least once a 6 is there. And the recommendation would be, if you have to calculate probabilities and you're not really sure, try to figure out this set. You could start by just playing around and try to write down all possible elements in the set which are there. So you could start first dice has the 6, and then find out how many possibilities you have to do this, and then the second dice would be 6, how many possibilities you have, and you have to include, of course, cases where the first is also 6, because only one has to be 6, and so you continue. Find a clever way how to enumerate this and find the size of the set. But sometimes these rules, what we had here in the last slide, they will help us to make such calculations more simple. For example, in this case, we could just calculate what's the probability of the complementary event, and what's the complementary event? The complementary event AC, and the complementary event is the event that there is no number 6 at all. And so when we take our rule, the probability of event A equals 1 minus the probability of this complementary event. And now the trick is that the probability of the complementary event that no number is 6. So this is now all 4 dices are independent. So the probability that one dice has no number of 6 is 5/6. And now we have independent events, we can multiply them, and then we have the simple rule 1 minus 5/6 to the power 4. And if you calculate this is 671 over the year 2000, 1296, and this is a bit larger than 1 over 2. So these rules that we showed you here, they help you very often to calculate events, and so calculating events very often means very good counting of complicated sets, and in doubt try to really enumerate all possibilities and find a way to count them. So that's for the moment, and in the next video we go to conditional probabilities, and then we will see examples where our intuition about probabilities easily can go wrong. So that will be then a bit more interesting. Okay, for now, thanks.